Good evening. Welcome to today's public lecture. I'm Sanjeev Arora, a visiting professor here and a professor in computer science at the university. And it's a great pleasure to introduce tonight's speaker, Chris Manning of Stanford. Chris is one of the experts in our understanding of language and how to make computers understand that language. He started in linguistics, which is the traditional field that studied language, and then at some point transitioned into computational linguistics, which is how humans and machines can converse in language. So Chris has been in this field for a long time, and he's one of the very few people who's managed to adapt to all the new changes that happen. So in the previous computer science boom, which you may remember, the boom in the late 90s, was around the World Wide Web. And out of that came entities like Google. And at that point, Chris wrote a very foundational book on information retrieval, which became an important text. And lately, the new boom in machine learning and computer science has been driven by a tool called deep learning, which he'll talk about tonight. And there again, Chris was very quick to recognize its potential and develop it further. So he's one of the leaders, maybe the preeminent leader in this field. So it's a great pleasure to have him here, and I'm sure you are in for a treat. His talks are always wonderful.
Good evening, and thank you for coming. So this evening I want to tell you a little bit about the recent successes and future prospects for deep learning, which is the re-emergence of the method of neural networks for the purposes of language understanding and cognition. In the last few years, machine learning in general, and in particular deep learning systems, have achieved enormous success in sensory perception tasks. We have taught computers to see an image and understand the objects it contains. We have also taught our machines to hear our voice and to recognize the words we have said. The speech recognition on your cell phone now is incredibly good at hearing and recognizing the words that you have said. However, recognizing words is not the same as understanding them. Commonly on your cell phone, the words that you said are recognized, but all you then get beyond that is, would you like me to do a web search for those words? And moreover, intelligence is not only about perception tasks. It is also about understanding and reasoning over human knowledge. Today, most of humankind's knowledge or information is available in written form, in books, or increasingly in digital form on the internet. And so a really central question for artificial intelligence is how can we teach computers to comprehend human language so not only can our computers interact better with us, but also so the knowledge of the world that we have accumulated so far is accessible to them, and so they can interpret and reason intelligently as we can. Trying to understand human languages has a very, very long history. So many, many centuries ago, Aristotle did some of the foundational work in that direction. He sought to systematize things like the parts of speech of language, nouns and verbs. And he also worked on doing inference. So he's most famous for the notion of syllogisms, the most classic example of which is all men are mortal, Socrates is a man, therefore we can conclude that Socrates is mortal. It took a very, very long time for the understanding of language to move much beyond this point. And the central person who brought things further forward in the middle of the last century was Noam Chomsky. He was the first one that really realized that there was much, much more to understand about the structure of human languages, how they're learnt and how they convey meaning, than was known about in traditional philology or linguistics. So Noam Chomsky really redirected linguistics towards being a science in the 1950s and 1960s. And in particular, he argued that grammars are a well-defined mathematical concept that could be studied. as a result of that, Noam Chomsky made not only huge contributions to linguistics, but also to computer science. So the area of formal language theory, which underlies our modern programming languages, largely follows Chomsky's ideas. Many of you may also know that Chomsky has also been a long-term contributor to politics, but I'm not going to go onto that topic here tonight. I'm actually a direct academic descendant of Noam Chomsky, and if I just quickly tell the story of this, I guess we can see the movement over the generations from the humanities towards the sciences of engineering. So if we go back a few people, this is Hermann Hilbrecht, who was a German-American Assyrian archaeologist. He dug up Assyrian stuff in Iraq. So one of his students was James Montgomery. He wrote his dissertation about the Samaritans. Again, largely history and theology, but starting to move into also looking at their writings and literature. One of his students was Zelig Harris. Zelig Harris wrote his dissertation as a grammar of the Phoenician language, so he was a linguist by this point. And really, Zelig Harris was a very important precursor of Chomsky and really started to develop the idea of perhaps we could study mathematically the structure of human languages. So Chomsky was his student, and one of his students was Joan Bresnan, whose major contribution was trying to say that we should be looking for grammars of human languages which are much more psychologically informed and real. And then that leads down to me. When I was a kid, it was the era in which people used to play text adventure games. Now, when I showed this example to my host, Sanjeev Arora, he said, "Oh, no, that's way too geeky. No one will know that." But I insisted on keeping the example anyway. Did any of the people in the audience remember? Yeah, a couple of, oh, hey, there are quite a few people who remember these. Okay, great. Yeah, so there used to be these text adventure games on early computers, right? So it said you were standing in an open field west of a White House with a boarded front door. There's a small mailbox here, and you could type something to say, like, open mailbox, and it said, opening the small mailbox reveals a leaflet. And then you could say, read leaflet, and you started into the adventure of the game. Okay, so it was interpreting what the person typed for very simple things here, like open mailbox. So the pioneering game adventure used a simple two-word grammar. So I can use this to introduce formal models of grammar. So you could say things like get lamp and cross bridge. That's all you could say. So it had a grammar where a sentence went to a verb and a noun, and then you could have verbs like get or cross, and you could have nouns like lamp or bridge. And so we can think of the structure of sentences according to this grammar by putting a tree structure over them, so that a sentence goes to a verb and a noun, and then the verb can go to get and the noun to lamp. And so that's the kind of context-free grammar structure that we often put over human languages. Little kids also often go through a two-word stage, except their two-word stage is less tied to particular parts of speech. So they will certainly say things like want juice, but they might also just say me potty as a different kind of two-word utterance. Okay, so the game I showed a minute ago, Zork, which was a very successful game at that time, crucially what its authors wanted to do was to have a system that could understand and parse a bit more of natural language, here English, than just those two-word utterances. So you could say things like get the lamp, get the brass lamp, or get the lamp and keys. And so they proceeded to be developing a more complex grammar of English. So now the verb could be followed by a noun phrase. And then we start to see one of the distinctive features of human languages, that you can get this recursive structure in terms of more complex units of itself. So a noun noun phrase can expand as a noun phrase and another noun phrase. So if we look at the final example for get the lamp and keys, our sentence can now parse to a verb and a noun phrase, and that noun phrase then expands as a noun phrase and noun phrase. And then we had other rules for a noun phrase, so now rather than just noun phrases that are only a noun, we could build a noun phrase that's also an article and a noun, or an article adjective and a noun. So we could say things like get the lamp or get the brass lamp and the keys, and that these would all parse. When I was a high school kid, having adventure games like this seemed completely fascinating to me, so I set about writing my own programs to try and parse up these kind of simple utterances on my TRS-80 computer in those days. But the funny thing was that when I was a grad student, I got a internship at Xerox PARC, and essentially what they were paying me to do a decade or so later was effectively exactly the same thing, to handwrite rules of grammar like this to be able to parse up English sentences. And it was really doing that for a couple of years as a grad student that made me think, surely there must be a different, better way to start thinking about getting computers that understand language than me having to type in all of these rules of grammar. And that's kind of what set me down on the path of then trying to look at machine learning approaches for understanding grammar. But before I move away from Zork, I just want to quickly flash up. Obviously, sort of having this structure for a sentence, that isn't enough to be able to have something like a text adventure game. You also actually have to know what words mean and have them operate in the world of the game. And I don't want to go into the details, but I just want to mention that that's then moving us into the area of semantics, the meaning of language. And the way semantics was done in Zork was it was also completely and laboriously hand-coded. You don't have to understand the details of this. I don't understand the details of it either, but effectively a programmer was writing pieces of code for every object and every verb, working out its actions. So this is things that you could do to an avocado, and if something you do to an avocado was eat it, and you can then see in those tell statements the pieces of text that would be being sent back to your screen if you took that operation, or instead you could cut open the avocado and get a different action. And then the other bits of what's in there are then updating the world state to reflect the operations that you've undertaken. Okay, so that's what I started doing as a high school student, and it was what I was still doing as a PhD student. I think at the beginning this seems a really great enterprise, because you can start writing a grammar and every day you can parse more stuff, and it seems like I'm moving along and starting to produce a computational implementation of English or whatever other language you start off with, and this seems a reasonable way to make progress. But as people started to do this more and more at a larger scale, it seemed like this really isn't going to work. And it's sort of hard to really capture why it's not going to work, but it comes down to a whole bunch of factors that has to do with how large, complex, variable, and squishy human languages are. That it's extremely, extremely difficult, that you seem to be making progress for a while you have a small grammar, and then as you start making your grammar bigger and bigger, you just end up falling into this morass, and it's almost impossible to make further progress. And so these are some of the things you have to deal with, that languages are human languages, not programming languages. Human languages are highly ambiguous at all levels. They're variable, they have recursive structure and co-reference, they exploit context to convey meaning, they're fuzzy and vague. You don't only have to understand language, you have to understand how the world works to interpret language often. Languages are a social system. A lot of what's going on is subtler social cues of persuading, insulting, amusing people. So it's very difficult understanding languages. I thought I'd give a couple of examples. One of the first things that you can notice about human languages is they have a lot of ambiguity between words and their reference. And so you can both have ambiguity and synonymy. So here are some objects, and if we look at that Coke bottle, you can refer to it by many names, some of them slightly dialectal. So you can refer to it as soda, soft drink, pop, beverage, Coke. So often we can refer to an object by many words. Conversely, many of those words have various meanings. So pop can refer to popping a balloon or your father or the pop that is soft drink. So we have this hard many-to-many interpretation challenge. If you move up a level and look at the structure of sentences, human languages, again, aren't designed to be unambiguous. They have a lot of ambiguities. I put up a few examples here from newspaper headlines that illustrate in a humorous way how we get ambiguities. Okay, so here we have boy paralyzed after tumor fights back to gain a black belt. How is that ambiguous? Well, so there's one sense in which the tumor fights back to gain a black belt, and that paralyzes the boy. And so all of tumor fights back to gain a black belt is embedded after the after. And then there's the other meaning, which I think is the one that the writer intended, which was it was a boy who was paralyzed after a tumor, so that's a relative clause modifying the boy, fights back to gain a black belt. And so while there are ways in which you can make things more explicit in English or any other human language, and lawyers, etc., variously try to do this, but the way English is normally used, we just live with these ambiguities and we understand each other perfectly fine. Here's a couple more examples. San Jose cop kills man with knife. In terms of the structure of the sentence, it's completely ambiguous as to whether it's the man has a knife or whether the cop is using a knife to kill him. The Pope's baby steps on gays. But it's meant to be read as the Pope's baby steps on gays. There's an interesting fact here that some of these ambiguities are actually disambiguated in spoken language. So in spoken language, you'd definitely pronounce these two differently. But that's not true of the preceding example with the San Jose cops kill man with knife, which probably wouldn't. So we have, there's difficult language interpretation problems here that we have to deal with. So those are... these are fairly clear examples, and so they're easy, precise ones to say that things are hard. But I think in a sense that they don't actually capture a lot of what's going on. So if I can just have a moment of deference to the fact that I have a humanities PhD, I think a lot of what's going on aren't those sort of very clear, precise ambiguities, but much softer things of interpretation. And so I thought maybe I could try and illustrate that by this nice XKCD comic by Randall Munro, which sort of talks about the softer side of language. The writing is very small, but hopefully I can about read it on my screen. So one of the two says, "Anyway, I could care less." And the other one says, "I think you mean you couldn't care less. Saying you could care less means you care at least some amount." And then the first one says, "I don't know. We're these unbelievably complicated brains drifting through a void, trying in vain to connect with one another by blindly flinging words into the darkness. Every choice of phrasing and spelling and tone and timing carries countless signals and contexts and subtexts and more. And every listener interprets those signals in their own way. Language isn't a formal system. Language is glorious chaos. You can never know for sure what any words will mean to anyone. All you can do is try to get better at guessing how your words affect people. So you can have a chance of finding the ones that will make them feel something like you want them to feel. Everything else is pointless. I assume you're giving me tips on how you interpret words because you want me to feel less alone. If so, thank you. That means a lot. But if you're just running my sentences past some mental checklist so you can show off how well you know it, then I could care less. Okay. So, if I was going to stop handwriting my grammars, how could I start to do better and more for learning about languages and their interpretation? So starting in the 90s, people started thinking about these ideas, that to interpret languages, we need to have knowledge about language and knowledge about the world, and we need a way to combine that knowledge. And often that knowledge will be partial and uncertain. So maybe what we should be doing is building probabilistic models of language. So the idea is if we could start to, this example is from translation, look at French and English and how it was translated, we could see when the French said maison, there was generally a translation to house in English. So you'd say that with high probability, maison gets translated as house, or maison means house. Whereas when someone writes l'avocat général, despite the fact that l'avocat can mean avocado in French, you shouldn't translate that as the general avocado. So that will then be given a low probability, and a different translation of being advocate general or something like that would be given high probability. And so this idea of putting probabilities over pieces of language turned out to be a really useful idea that's allowed us to do a lot of things. And one simple example that's been widely deployed is using it for spelling correction. So here's a sentence that someone wrote: she is a stellar and versatile actress whose combination of sass and glamour attracts. Looks like they made a spelling error. And then the question is, well, how can we correct that? And so we might think, oh, they got most of the letters right, so we might explore adding one or subtracting one or changing one, and then we might be able to correct it. But it turns out there are lots of things you could change it to. So from a cress, I could delete the first A and I get cress, that's a kind of green stuff. Or I could delete the final S and get acres. I could change the E to an O, a cross. Or you've probably guessed, I could insert a T after the AC and get actress. But how are we going to choose which of those mistakes the author made if we're a computer? And the idea that started to gain traction was, well, maybe we could look at how likely words are to follow each other. So after the word versatile, are you likely to say cress, versatile cress? Maybe not. Whereas versatile actress, that sounds much more reasonable. So if we could estimate those probabilities, maybe we could choose corrections. And so that's what Google did for their spelling correction, which is part of why Google spelling correction works so great. You just type some letters into the search bar and it decides what you probably meant to spell. It was also introduced into other things like Microsoft Word since 2007 had this kind of context-sensitive spelling correction, whereas before that there was literally sort of a dictionary and you could look up whether the word occurred in the dictionary or not, and then it could tell you just words that were close but wasn't able to choose one for you. So probabilities say how likely something is. And in general, you're probably more used to seeing probabilities for sort of numeric science things. The probability of rolling a 6 on a standard die is 1/6, or the probability of rain is 30%. But it turns out that we can put probabilities over any bit of human language and therefore mix the sciences and the humanities. So we'd like to know the probability of a piece of language, like she is a stellar actress. And so we're just going to have a sequence of words, word 1, word 2, word 3, and want to give a probability to those. Now that seems like it's going to be kind of hard, and we can begin to make sense of that by using a notion of generating the words one at a time and look at their probability of following each other, what's called a conditional probability. So if I want to work out the probability of a sequence of words, I can first of all work out the probability of word 1 starting the sentence and ask, well, what's the probability of the second word following the first word? What's the probability of is following she? And then ask, well, what's the probability of following she is? And generate words and come up with probability estimates one at a time. Yeah? So you could think that you want to do that, but you actually don't need to, because they'll be kind of factored in afterwards when we're then working out the probability of the next. So, when we're generating word 3, we're just doing it based on word 1 and 2, but when we generate word 4, we're then conditioning on 3. So we're sort of considering that one backwards in our generation. And this sort of seems to make sense, because humans do both actually say their sentences and the listener comprehends them, just sort of working from left to right. Okay, so that seems like we might be able to make progress. So if I then want to say, well, how likely is the word actress to come after a stellar and versatile, I could naively say, that's easy. All I'm going to do is find a really large amount of text. There's a lot of text on the World Wide Web. And I can count up how often I see a stellar and versatile in pieces of text. And then I can look at all of those places and say which words followed that word. And effectively, I want to work out, what proportion of the time actress followed a stellar and versatile. And so I can do that by counting up how many times I saw a stellar and versatile actress and dividing it by the number of times I saw a stellar and versatile. And that'll give me the proportion of the time, the conditional probability of actress following a stellar and versatile. In principle, that's easy. In practice, that's impossible. If we assume a vocabulary of 100,000 English words, which isn't that large, right? The kind of, those dictionaries that are that thick that sit on your shelf, they'll typically have something more like 300,000 words listed in them, right? And then if we say, well, how many word sequences of length 5 are there? That means there are 10 to the 15th, a quadrillion. So it seems like we're in bad trouble if we're trying to count up 5-word sequences, if we counted over, a pile of text that might be 1 billion words long. We've still got far too many things to estimate. So commonly what people do is make a simplifying approximation where we say, let's try and work out the probability of the next word just based on the one preceding word. And then I'm in a space that I can easily count. So if I want to say, what's the probability of the word versatile following actress? I go to my source of a lot of words. So you can find on the web the corpus of contemporary American English, which will give you counts for this easily without even having to count it for yourself. And so versatile in that corpus occurred 2,717 times, and versatile actress occurred 6 times, and so that gives me a probability of versatile following actress. You can note even there that those counts aren't huge now, but they're large enough I can get probability estimates from. Okay, so that gives me the ability to do this context-sensitive spelling correction. So if I just consider 2 possible candidates, like what's the chance this word is actress versus what's the chance this word is across, what I find is that actress is much more likely to follow versatile than across is. But also, actually, whose is much more likely to come after actress than it is to come with across. And so if I then multiply those 2 probabilities as I sort of generate along the sequence, I find that the probability of correcting it to actress is about 3,000 times more likely than the probability of correcting it to across. And so I can choose that correction. And interestingly, it's now choosing a correction which isn't just the most common word. So if you also do these counts in the corpus, you find that the word across occurs in English about 10 times as often as the word actress. That's not surprising. Across is used in a lot more contexts. And so it's correctly able to choose a word that's less common overall because it's more common in context. So that's an interesting demonstration of the usefulness of probabilities. And this is where many people feel that Noam Chomsky kind of went wrong. That although Chomsky wanted to understand human languages and both the structure of human languages and the central questions of human language, which is how do little tiny 3-year-old human beings start acquiring these languages, and how do human beings of our age understand each other when we talk. Effectively, Chomsky got all consumed by looking at the sort of structure of grammars of human languages, which he felt had a logical structure. And so he famously said in 1969, but it must be recognized that the notion of probability of a sentence is an entirely useless one under any known interpretation of this term. And many people feel that that was very badly misguided. In fact, about 15 years before Chomsky, Claude Shannon, who was a famous early information theorist, he essentially invented information theory, but also did pioneering work on artificial intelligence and machine learning. He wrote one of the first successful machine learning systems. That he essentially developed the notion that probability gives us a really good tool for understanding what is likely to have been said or meant. And what we have found is that when we want to do tasks like speech recognition or spelling correction or interpretation of ambiguous sentences, for any of these processing tasks, that probabilities have proven to be a very useful tool for making progress with language. Okay, so we've made some progress here, and it's sort of looked good, but you maybe shouldn't have been convinced that things totally looked good, because, you know, even when we were just sort of predicting based on the previous word, well, if there are about 100,000 different words, that still means that there are 10 to the 10 word pairs that we might want to find out probabilities for. And so it still seems like we've got problems estimating those probabilities if, in my corpus of contemporary American English, I actually only have 500 million words. I've got well less words than the number of pairs I want to estimate probabilities for, and really I'd like to have seen each a whole bunch of times to come up with an accurate probability estimate. So I still have problems. Now, there are many ways that you could work on this, and in the sort of period from about 1980 through 2010, people came up with lots of clever statistical methods of doing estimation that in practice worked pretty well. But what I'd like to move on now to is to get us into the area of using deep learning style techniques for language. And so to do this, we make it a rather radical move, which seems to take us much further from everything that we thought we knew about language, which is to say, well, before we just had words, that seemed fairly uncontroversial for how languages work and put probabilities on them. But now why don't we say that we're actually going to represent a word by a vector, a list of real numbers. And in this picture, there are 8 real numbers, but typically actually it might be a 100-long list. And we're going to say this is the representation of the word versatile. And so then if we're going to try and work out probabilities of words following one another, we're going to say, well, another word like actress also has a vector of real numbers. And we're going to say that it's going to have a high probability of following that word if these two vectors are similar to each other. So you can look across the rows and say, well, these vectors are sort of similar. Both of them are big in the second number. Both of them are negative in the third and fourth number and positive in the fifth number. They're sort of similar vectors, so there should be a reasonable probability of this co-occurring. And this will be a useful notion if words that are similar in meaning and therefore similar in co-occurrence tend to have similar vectors. So we might say, well, what happens when we have actor? Well, actor's got a slightly different vector, but its vector is kind of similar to actress's. You know, big positive second number, a couple of negative numbers goes positive again, and so therefore it will be predicted to have a similar probability of co-occurrence. And so what we'll change things to is now saying, can we learn vectors for words which will be good at predicting their probabilities? Why does this help? It sounds like it's made a lot more complicated, but this can technically help because we've now got a lot less numbers to learn. Before, I said we still had to learn 10 to the 10th probabilities, where now if we've got a 100-dimensional vector for each word and there are only 100,000 of them, that means we only have to now learn 10 to the 7th numbers. So we only have to do 1,000th as much work as we had to before. So that's progress. It gives us other ways we can make progress. It turns out that there are really easy ways to learn these vector representations of words that work very well. And actually, it also solves the other problem of estimation, that we'd like to remove the assumption that we're only estimating probabilities from one previous word. And once we have these vectors, we can very easily start to condition probabilities of the next word on many preceding words without making our estimation problems any more difficult, because we're now all in the space of numbers rather than having these rare word symbols. And so effectively our problem is that if we have symbols like words, hotel and laptop, the problem with them is that they don't have any inherent notion of similarity. So if we think of web search, if a user searches for Dell notebook battery size, we'd like to match a document that talks about Dell laptop battery capacity. But you know, they're sort of different words, notebook, laptop, size, capacity. You and I know they mean similar things, but if they're just symbols, they're just different symbols that have no inherent connection between them. And so it would be useful if we had a representation of words that inherently show which words are similar in meaning. And that's precisely what our numeric representation of words will do for us. So how can we go about building these representations? There's been a very influential idea that's used everywhere through computational linguistics, which is the notion of using distributional methods to learn similarities. It's sort of a simplification, but it works incredibly well. It's usually attributed to this British linguist, J.R. Firth, who said, "You shall know a word by the company it keeps." So we want to learn a meaning for the word laptops, and so what we're going to do is look in our same big corpus and find lots of pieces of text where the word laptops occurs. And what we're going to say is, well, we're going to represent the laptop by those words that occur in its context. So we see web browser, tablets, smartphones, home computers, Microsoft. All of those words are going to contribute to the representation of the word laptop. And so the way we're going to formalize that is by this same idea of having a probability of a word co-occurring with another word. But instead of just generating the next word, we'll do it for all of the words in a close window of context. So we'll try and predict words in the context from the word in the center. And so we're going to turn this into a model using our word vectors. This is the only scary equation in this talk. So what we want to do is have a way of having the probabilities of words co-occurring in terms of our word vectors. And how are we going to do that? Well, first of all, when we have these two word vectors, we're going to calculate a dot product. And the dot product means that we go across the rows and we multiply those. And so if both of them are big and of the same sign, we'll get a big positive thing. And if they're of different signs, we'll get a negative thing. And so we'll get a bunch of numbers which we then sum up. So our dot product will be bigger if the words are more similar, if they're sort of pointing in the same direction. And so that gives us a sort of similarity measure. And so what we want to do with that is we want to turn it into a probability. And so that's the rest of this scary expression. But it's not actually so scary. We call this a softmax. But it sort of does what you'd expect. So for the dot product, we have a kind of a similarity measure, but it's just a number. It could be positive, it could be negative. And so we want to turn that into a probability, a proportionate things of the time. So in the numerator, we exponentiate it, because if you take the exponential of any number, it becomes positive. And then we can always turn things into a probability distribution by taking the probability of every possibility, every different word that could follow this word, and summing those numbers up and dividing through. And that then normalizes to give a probability. Okay, so now we have a way of calculating probabilities in terms of our word vectors. But how do we learn the word vectors? And this is really interesting, and it's almost like magic how well this works. So what we do is we say, okay, for every word, we're going to have a word vector for that word, 100 real numbers. We have no idea what they are, so we're just going to initially set them randomly to small numbers. And so we have, if we have 100-dimensional vectors and 100,000 word vocabulary, we've got these 10 million parameters, and we just set them randomly to little numbers. And then we say, well, what we want to do is optimize these parameters so they correctly predict probabilities. So since we can count over a corpus, we know what the probabilities of co-occurrence of words should be. And so we want to change all of these numbers so that they will predict correctly. And so this kind of estimation is the bread and butter of modern machine learning and deep learning. So we don't know how to set the numbers, so we set the numbers randomly, and that starts us at this point here up in the red. And so then we want to accurately estimate probabilities, and so we have an error term which is how off the probability we estimate is for actual words that we find. And so we can measure that error, and what we want to do is find a way of moving downhill in this space in terms of the parameters that we can adjust, which are all of the elements of our vectors. Now, in this picture, there are only 2 parameters because that makes it easy to draw for us. But in our actual model, we have 10 million parameters. But conceptually, we're doing the same thing. We're going to fiddle all of those 10 million numbers to make this error go down. And so we just run this optimization. So empirically, what we do is we find a word in its context. We work out those probabilities and say probability of windows occurring near laptop. Our model currently says that that's 1 in 100, but actually the count turns out to be higher. There's an error term. Okay, we need to change those parameters. We change the parameters a bit to make it closer to correct, and we just repeat over and over again by randomly sampling different words and updating their parameters. That sounds like a dumb, easy process. But the truth is, with no more technology than that, if we just start at a random place and repeat this updating of the numbers millions and millions and millions and millions of times on our fast computers, that it's almost like a miracle occurs, and we end up with word vectors that represent the meanings of words and will predict probabilities really well. So what we end up with is a kind of a word space. So these word vectors appear as words in space, and really it's a 100-dimensional space, so we can only sort of draw a sort of 2D projection. And here you can't see anything at all, apart from there are a lot of blobs, but we could sort of zoom in a bit, and then we can zoom in a bit further, and hopefully now you might be able to read it. At least I can read it. In the top right there, we have sort of nationality words, right? Norwegian, Austrian, Danish, Dutch, Hungarian, and then the sort of historical peoples appear as a group down the bottom here, right? We have the Macedonians, the Greeks, and the Egyptians, and the Romans, that words sort of group together in similarity in quite amazing ways, so that we have a really good model of word meaning. And so then we can sort of just ask questions. We can say, okay, in this model, what are the nearest words to frog? And the nearest is frog, sounds hopeful. The nearest after that is toad, sounds hopeful. After that, my scientific knowledge fails, but it turns out a latoria is this really cute green tree frog, and that's a Leptodactylidae, rana. So it sort of just learns the meanings of words in a very good way. It doesn't only learn overall meaning similarities, it also learns components of word meaning. So you can find that these spaces have components of meaning embedded as linear vector differences. So here's the sort of direction between countries and their capitals, and you can see that that's almost a linear projection that you can project out of the space. And so you can do really interesting things with these models of looking at word meanings. Something interesting that you can do is actually show how the meanings of words change over time. So for these examples, here's the word gay, and around 1900 it means sort of daft, flaunting, and it starts to move, and so in the 50s it's sort of witty, bright, frolicsome. And then it sort of moves very clearly as we head to the end of the century into its modern meaning. Broadcast is another example, right? So in the 1850s, what you did with broadcast, you were sowing seeds, you broadcast the seeds, and then that started to move into the sort of modern meaning of television and radio. Awful's an interesting word, right? So in the 1800s, awesome was solemn, majestic. Awe was sort of like solemnness. It then generated sort of a bad meaning, horrible, terrible, but then, it's starting to sort of move to sort of in a more positive direction, it seems, as time's going by. And it may well end up positive, right? Some of these other words, so, related to terrible, we have the word terrific, which also originally meant frightening, right? It terrifies you, but it's completely flipped to now have a positive meaning of great. And so if you believe my picture here, wait another 30 years, and the word awful, you'll be able to say, that's an awful movie, and it'll mean it's great. Okay. So what does this mean for heading into how we think? So traditionally, people have suggested that when people think about how does the brain work and how do we think, people have traditionally had in their mind that maybe what we do is we take the symbolic system of words used in language and we project them back onto the brain. So philosophers for centuries have talked about the idea of the language of thought, assuming that thought proceeded in a way that's kind of like our human languages work. But actually, if you look at brains, the brains seem to have a continuous pattern of activation, which you might model with real numbers. And so deep learning is effectively exploring just this kind of continuous encoding of thought. A continuous encoding, which is sort of like the signals that are used to send language across to other people. So a speech signal is also a continuous encoding. So we seem to have this pattern where where brains have this continuous encoding. It then goes through a symbolic encoding of language words into a continuous encoding for transmission. And so a central cognitive science question is to what extent we really have symbolic representations that we use to think within our brains, or do we actually directly think in terms of the continuous substrate that brains seem to have at a lower level? And essentially the idea of neural networks and deep learning is built in a metaphorical way based on this continuous substrate of brains. Here we have a neuron, and then we have 3 other neurons that are sticking into this neuron. And so what we have in our brains is that we will have the output of one neuron will feed into the dendrites of the next neuron, and there's the point where there's a little gap where they join, which is then when the synapse is. And so that if a strong enough signal is sent down from this neuron, it'll then cause a firing over the synapse and will feed an input into the next neuron. And so this neuron will then kind of collect various inputs on its dendrites to get a signal, and it will then be able to positively respond to some inputs, negatively respond to others, and then at appropriate moments it will then send a signal of a certain strength down its axon to the next neurons that it connects to. And this is essentially the kind of model that we are building in a sort of a simplified, regularized form in our neural networks. So when we build our neural networks, we have our inputs for a computation, which are these real numbers. Then each of those is given a weight, and this is where we're then sort of multiplying the 2 numbers as a dot product. So it can either say, I'm positive, and so I'll increase my firing chance with this number. I'm negative, so I'll be more likely to fire if x2 is also negative. So we sum up these dot products just like we did in learning our word vectors. And then again, we have some kind of modulation of the sum as an activation function, and that we send out our outputs. So when we build our artificial networks, that we essentially take a whole bunch of these artificial units and connect them together and build our deep learning systems out of them and use them to predict. I'll skip a bit. And so as we go forward in neural networks, we can then build much more complex neural networks that combine together vectors and multipliers of numbers and do complex things. And so the amazing thing is it's turned out we can not only do simple things like word similarity, we can now use these neural networks to do things like feed in a sentence in one language, where we feed in word vectors and the current state of the machine, and we do the same kind of math operations of multiplying, adding, and putting through a function, and calculate a state of a sentence that as we feed through the sentence will then allow us to generate a meaning of a sentence so we can build a translation out the other side. I mean, in practice, we make it more complex than that. Rather than this kind of shallow network, we do deep learning with a deeper, more complex neural network. But essentially, this idea has worked really well and has allowed us to progress forward with tools like machine translation. So there was an earlier generation of statistical machine translation systems, and these have been some of the universities in Europe that have had very good machine translation systems. But the development of using neural network methods for problems like translation just has allowed us to make much, much better translation systems. So our neural machine translation system, this particular evaluation, made over 25% less errors than the other systems. And so because of that, these neural systems have been an enormous success. And so this was really a very quick technological deployment, that the first neural network systems for machine translation started being explored and researched in 2014. But 3 years later, all the big commercial technology companies have now switched over to using these systems in their operational machine translation environments. So we really live at the moment in a time of very exciting and very rapid progress in AI. It seems like as every month is going by, we're finding new and exciting things that we can do with machine learning, and particularly these deep learning artificial neural network methods, that the idea of sort of training models on a lot of data has just allowed us to solve many problems that I think people never thought would be able to be solved in those methods. One could wonder if that's all that's needed and we're on our way to the artificial intelligence singularity of superintelligent machines. I suspect that that's not true. I suspect that there is still more things that we fundamentally need to work out, that these neural networks are very good at sensory perception and they're very good at matching, but I think we probably still have more to work out for how to model knowledge and reasoning. And a lot of the models, like the neural machine translation models, don't actually make very much use of the structure of language, that rich structure that Noam Chomsky has spent his life trying to elucidate. And I think we'll also start to need to make more use of structured representations, partly for language, but also for other areas of cognition and visual representation. And so those are still ideas that I think there's work to do on the future. Thank you.